meeting is being recorded.
Okay, welcome everybody to data mining. Hope you all had good weekends, good Halloweens. Hope you're all ready for the upcoming midterm. Maybe this week will be more scary than Halloween was for most of you. Today, a couple quick announcements here. So there was a post about wanting to do another review session. I thought our last review session on Friday went pretty well. So this Tuesday, 9 to 11, normal office hours time, we'll have a dedicated midterm review session for people who want to participate in that. And then also sort of related to that is that Friday morning, because I've had a bunch of dedicated office hour sessions for this class, my other class that I'm teaching wants some attention, and so Friday morning will be for the other class. And last time too, during the midterm week, this was not really heavily attended by this class, the Friday office hour. So I don't think that's too much of a, I don't know, compromise. But the important thing, Tuesday, 9 to 11, other midterm review for this class. Today in class, we'll continue going over one other announcement. So preparing thing for the exam here. The last exam, I put together this list of common bad habits that people had when going through the whiteboard, your presentations. I'd recommend just reviewing this list again. It's in our repository/exams. A good thing to just read through for 5 or 10 minutes before you end up doing the exam this week. Let's see. So today in class and last time in class, we started going over this notes optimization.pdf. Today we will continue going over the notes optimization and possibly finish it, possibly not. My intent is for us to be going at a mostly relaxed pace. At least for me, it feels like a relaxed pace, talking about this optimization stuff, since you all have the other probably more weighty thing on your mind of the midterm material. And some of the things I tried to time our discussion of this optimization stuff, because there will be things that we'll be talking about today that will also be somewhat review of the material for the midterm. So hopefully it's not, it'll still be worth paying attention, and it's not too hard to pay attention. Any questions about anything administrative though before we get started on technical main class stuff for today? Everyone's ready for the midterm? Excited for the midterm? Yeah. That's a fair response. Okay, so our notes optimization. Again, we're big picture idea here, going over this, or one of the things that we're building up to is being able to talk about stochastic gradient descent, especially as presented by this paper here from Leon Bateau. And actually, one more fun thing that I want us to do before we get into the meat of this notes optimization again. You've probably all seen Google Ngrams before for different things. I thought it would be fun for us to talk about some of the history of all the different terms that we've been talking about so far. So calculus, again, invented in the 1600s. And so if we did Google Ngrams for calculus or derivative or integral, you'd see a straight line basically since 1800 to today. People have been using those terms. Eigenvectors, so we talked about those starting with the PageRank. They have been used since the early 1800s, 1700s. The term eigenvector, though, actually came about in World War II, and so you can see the green line here coming from World War II. And PageRank here, being invented by our Google founders, Brin Page, in the late 1990s, 1997. You can see that as PageRank was invented, became more popular, the word eigenvector became less popular because people now, instead of talking about computing the top eigenvector, just start talking about computing the PageRank. And this idea of power method, this algorithm for power method, it was invented in the 1920s, right around here. And you can see that it has a mostly straightish line of people talking about the power method. The VC dimension, though. So VC dimension invented in the late 1950s, early 1960s by Vapnik and Chervonenkis in the Soviet Union. But because they speak Russian, and this is an English search right here, and people in the US not only speak English, but basically don't speak Russian. We didn't know about the VC dimension until the late mid-1980s when the Soviet Union was opening up, and then the VC dimension became a super popular tool in the machine learning community over here. And you can see that the peak of popularity is around 2000, and then it starts going down a little bit. That's not because the VC dimension is out of date or anything like that, or it's not used anymore. It's just because there are other notions of complexity that start becoming invented, that become more powerful, more useful. And so people talk about them a little bit more. But the captures the same idea plus other things. One of those notions of complexity here is the Rademacher complexity. It's sort of the most famous, powerful one in use these days. And you can see that as the VC dimension is going down, again, not because those techniques are less important, but just because other things are invented that are starting to become also important. And then we talked about all of our feature maps and things like that. And this idea was first invented around 2000, again, at the peak of popularity of the VC dimension in 2000, and invented as ways to control the VC dimension. The textbook uses the phrase polynomial feature map or polynomial function or map, and but in the main machine learning community, the word kernel is more commonly used. So here's the polynomial kernel. Principal component analysis, invented long before in the 1960s. Actually, right here, you can see that it starts becoming popular in 1960, exactly when the eigenvector starts taking up popularity. So PCA and eigenvector very closely related to each other again, because the matrix in your PCA is full of eigenvectors. But also then here, the decision stump gaining popularity or being invented here in the late 1990s as a way of controlling the VC dimension as well. Let's see. Then logistic regression and perceptron. So today we'll be talking more about the logistic regression and optimization of that function. It's existed since the early 1800s. People have been using things equivalent to logistic regression since then. 1960 is when the phrase logistic regression becomes popular, and statisticians start talking about logistic regression. At this time in the 1960s, computer scientists didn't know what logistic regression was. We only knew what perceptrons were. That was our main tool at that time for artificial intelligence, and very peak of popularity here in the mid-60s, and then you can see this decrease in popularity. This is called the first AI winter right here. People realized that the perceptrons, you could not optimize them because they are, again, NP hard to optimize the 0-1 loss. We saw that with some of these graphs last time. Like if you add all of the loss functions for all of our training points together using the 0-1 loss, like you're doing in the perceptron, you get something crazy with a bunch of step functions like this, and it is NP hard or exponential time in order to find the minimum of a function like this. And so people in the computer scientists in particular in the 1960s became very depressed about that and gave up on AI until the mid-1980s. The reason for that is because around this time is when it was discovered that logistic regression could be used as a surrogate for the perceptron or a surrogate for the 0-1 loss. And so logistic regression taking off in popularity, again, bringing the perceptron with it for a while. At this point, though, this is about 1990 right here. At this point, we didn't know, so we were just getting into the English-speaking world knowledge about this VC dimension stuff. We didn't know about these kernel maps going on and how to control the VC dimension at this point. And so when people realized that logistic regression and perceptrons were only linear functions and not able to capture more important information or not able to capture larger, more complex decision boundaries. Again, a new AI winter happened where you can see the perceptron not being talked about as much, but statisticians continuing to do their thing with logistic regression, and that's getting popular. The perceptron, again, seeing a resurgence in popularity around the this 2011, 2010, 2012 timeframe, where stochastic gradient descent starts being popular. Our paper right here from Leon Buteau, published in 2011. And this is really, this paper right here is the kickoff point for stochastic gradient descent being super popular. This last graph that I wanted to show us is about stochastic gradient descent versus gradient descent. So again, gradient descent, we started talking about this last time. We'll review it again here in a little bit, but it's this term first introduced in the 1960s, again, as a way of computing logistic regression. It was a combination of computer scientists and statisticians who developed this gradient descent method, applying it to logistic regression. But it was not artificial intelligence computer scientists who were working with gradient descent at this point. They were still focusing on the perceptron stuff and trying to find algorithms for the perceptron. It wasn't until the mid-1980s over here, again, when the perceptron is kicking off, there's this resurgence in artificial intelligence, the end of the AI winter. And this AI winter largely ended because of gradient descent, because people realized that you could use something like logistic regression or some other surrogate loss to optimize the perceptron and get good performance with your perceptron without having to do exponential computation. So gradient descent becomes super popular, kind of levels off here for a while, and then the 2011-ish timeframe is this breakout point for stochastic gradient descent. The main limitation of gradient descent, which we will see, is that it is hard to use on these large data sets, so where n is very large. And around this 2011 timeframe is when Facebook and Google and Microsoft, all of these companies are creating their very, very large data sets. This time frame often termed as like the beginning of the big data sort of era. And at that point, stochastic gradient descent becomes the algorithm of choice for optimizing these problems. And again, we'll see why that's the case here in a little bit. In around 2011 timeframe, gradient descent no longer means the 1GD algorithm that we talked about last time. And gradient descent is now basically a synonym for stochastic gradient descent. If people are talking about optimizing things with gradient descent and they don't put any qualifiers about it's specifically not stochastic gradient descent, then they probably are talking about stochastic gradient descent. That's how influential this algorithm has been. It's totally taken over the meaning of gradient descent. So that's our historical time frame building up to where we are here, 2011, Leon Buteau. Again, so on the last time we talked about this square plots like this with these step functions, hard to optimize, can't use gradient methods to do this, and exponential runtime to do this. But the logistic loss is convex, has this nice sort of shape that makes it easy to kind of roll downhill, no matter where you start at, roll downhill, and you'll eventually get to the obvious minimum of your loss curve. And logistic regression maintains this surrogate property where the in-sample loss of logistic regression is at least the in-sample loss of the 0-1 loss. And so by minimizing the logistic loss, we are also minimizing the 0-1 loss. And in particular, if we get good results with the logistic loss, that will guarantee good results with the 0-1 loss over here. That's one of the main takeaways from our discussion about why we care about the logistic loss. And again, this right here follows immediately from the surrogacy property. Surrogacy is not related to optimization, it's related to why we care. The key term that's related to optimization is convexity, that logistic loss is convex, which means when we sum many of these loss functions together, we're going to get a nice shape that we can get to the minimum very efficiently. So convexity, good for optimization. Surrogacy, why we care about doing that optimization in the first place. And the last time that we finished up talking about two algorithms for actually computing the minimum over here, this gradient descent, and 2 GD or second order gradient descent. And I had two graphs over here that we looked at, one in 1 dimension and a second one in 2 dimensions. And they both show the same information, show how gradient descent is working. That we start at some particular points and we use this iterative step size algorithm over here to step hopefully downhill until we get to the minimum down here. I have two equations written because the one in red corresponds to how the notation in the book, and the one in magenta down here corresponds to the notation in the Lian-Bateau paper. And the main difference between these two things, between these two equations, is the Greek letter that they use to represent the step size or the learning rate. In the textbook, they use this eta variable. This in with a little tail at the end is pronounced eta. And in Lian-Bateau, he uses this gamma variable. That's like fish swimming downwards is a gamma, lowercase gamma variable. Either of these two Greek letters is very common, and a lot of other Greek letters are also very common. But it's always a Greek letter that is the step size sitting in front of the gradient over here. The nabla, the upside down delta, this triangle right here with the point at the bottom, pronounced nabla, is the gradient symbol, and we're explicitly taking the gradient with respect to our in-sample error, or so again, the red notation up here, the textbook notation, the magenta notation down here, the Lian-Bateau notation. Here, Lian-Bateau has moved the gradient inside of the summation. Recall that E in has a 1 over n summation inside of it. And so the gradient over here, it's a linear operator, so you can move it inside of summations. And Lian-Bateau, in his notation, moved it inside the summation as applying it to this Q function. This Q is our loss function. The loss function, sometimes denoted by Q, sometimes denoted by the script L. They mean the exact same thing. They have the same semantics, but they take their parameters in a slightly different way. And in any event, whether you're using this red formula or this magenta formula, you're going computing the gradient and stepping towards the gradient in some amount. That amount determined by the Greek letter in front, eta or gamma. So again, those are called often the step size because it determines how large of a step you are taking. And if you have your eta or gamma variable set to too small of a value, that's what this black curve right here is indicating, where you're taking very, very small steps each time. And so it'll take you a long time to get to the minimum down here. And so we don't want to set eta too small. We don't want gamma to be too small. We want it to be a little bit larger where it takes us fewer steps to get to the minimum. But if we set these variables to be too large, then we have what's called divergent behavior. Our optimization diverges, and that's what's indicated in this green line over here, where we go so far off to one side that we totally overshoot our minimum. And then if we keep doing that, we'll continue overshooting, and we won't actually converge to the minimum. We'll go get a larger and larger value each time. So this is the one-dimensional picture that you should have in mind for gradient descent. And down here, this is the two-dimensional picture for gradient descent, where our sort of best value is this orange again, where we take reasonable step sizes, and then reasonable step sizes. In 2 dimensions, the way to think about your gradient is it's like the direction that you should go. The gradient tells you which direction to go in, and the step size, whether it's gamma or eta, tells you how far to go in that direction. So go every time, no matter what our gamma or eta variables are set equal to. Starting from the beginning, we'll start in the same direction, but we'll go different sizes, different lengths each time. And if we're too large again, eta too large, we will diverge, never going closer and closer to the center point over here. But if we're too small, the black line over here, it'll just take us a long time. We'll have a very smooth curve getting over to the center, but it'll take us a long time to find that minimum. We'll have to do our iterative algorithm many, many times. And so there's some sort of balancing act about getting the right value for gamma or eta so that we're in this orange case, where it'll never be just like one iteration and we get there because we don't know the exact direction from W naught, our initial starting point, to the minimum over here. But we want to get as close as we can with each step and make it there in as few iterations as possible. And there's no theory on the exact formula to use for eta or gamma. It's just sort of a trial and error thing to see what works and what doesn't. And that's where we left off last time. Any questions about anything so far? Yes.
So when you say it diverges, when you're saying like we diverge, like what definitively is diverging?
Yeah, the question is, what exactly is the definition of diverging? So first, I will define the opposite of diverging, which is converging. Converging means that your line right here eventually reaches the dot down here. So we talked about convergence with the PageRank method and the power method, and talking about how each iteration we get closer and closer to what our final goal was. And that is converging. Your algorithm is converging if you are getting closer and closer to this final goal, this minimum value right here. Diverging is any situation where you're not getting closer to the minimum. So with PageRank, we talked about diverging in that your eigengap had to be sufficiently large to diverge. You had to have some eigengap in order to converge. And if you did not have any eigengap, you would diverge. And in this case, you will diverge, meaning you will not reach the minimum if your eta gamma variable is too large. Good question. Any other questions so far? Okay. So 2GD, second order gradient descent, was invented to try to give us this optimal value, try to compute for us optimally the gamma or eta variables. Up top here in the standard gradient descent or one gradient descent, or just plain gradient descent, we have these scalar variables right here. Eta and gamma are scalars, so they're just single real numbers. But in second order gradient descent, we have this gamma variable right here. This is this like corner looking thing is an uppercase Greek gamma. This is the lowercase gamma. This is the uppercase gamma. And here the uppercase gamma is a D by D matrix. And it's calculated in such a way that you notice there is no learning rate anymore. There is no user-specified hyperparameter that we have to place right here in order to tune second-order gradient descent. Just computing this gamma matrix in the right way is going to do that for us. The picture over here, I'm going to now add a picture of second-order gradient descent on here. And I will see it's getting a little bit crowded, but I'll do it in magenta over here. And what second order gradient descent is, it's going to do two things for us in this picture. The first is it's going to give us, again, the optimal-ish distance that we should move. But also because this is a matrix over here, it's going to tell us change our direction just a little bit. So it's also going to improve our direction. That's not a very straight line. Something like this would be the first step of 2GD, and then like that, the second step of 2GD. So this magenta line in particular is what 2GD looks like. And so it's guaranteed to converge faster in terms of the number of iterations for two reasons. One is that it's always taking an optimal step size. Again, nothing to tune, nothing to overshoot or undershoot. And it's improving our direction for us. It's always going to somehow curve our gradient descent line so that it's pointing closer to the minimum. The downside of second order gradient descent, which we'll formalize here in a little bit, is this. We have this additional matrix right here. So there's additional computation that we have to do on each iteration. So fewer iterations, but more computation per iteration. The next family of algorithms, and maybe I'll pause this for a second, come back over to the Leon Bateau paper, and remind us where in this paper all of this discussion has happened at. So this first section right here at the beginning of 2, this is all just a quick summary of chapter 1 in the textbook, introducing their notation. Basically, every machine learning paper will have this 1-paragraph summary about what is their notation for the problem setup, and it's always just whatever the important pieces of information from chapter 1 are of our textbook in their notation. The main difference in notation from the Leon Bateau and our textbook is this this F right here. They use F for function. Textbook uses the capital H. That's the first main difference. The second is E without a subscript is RE out. E with a subscript is RE in, like that. And I think we mentioned those things last time. And then the discussion of gradient descent right here, section 2.1. This is all of the material that we just covered pictographically. And then 2.2, stochastic gradient descent, is what we will cover right now. So the difference between stochastic gradient descent and standard gradient descent is just the removal of a summation. Since the page over here is a little bit crowded, I'm not going to write on this page anymore. I'm going to just write directly on the paper over here. And the only difference between SGD and standard gradient descent is that standard gradient descent right here in front of this gradient symbol has a 1/n sum from I equals 1 to n up here. And so the basic idea of stochastic gradient descent is, instead of taking the gradient with respect to all the data points put together, let's take the gradient with respect to only a single data point at a time. And the hope is that this will improve our computation, make our computation faster. I'm going to scroll up to the gradient descent runtime here, or the gradient descent formula right here, so we can talk about the runtime. One of the things that we said last time about where we ended was that the gradient with respect to Q is going to be from R to the D into R to the D. In general, Q is a R to the D into R function. And when you take the gradient with respect to a function like this, notice that the type here changed so that the output is no longer a scalar. Our Q, our loss function, takes a vector as input and outputs a scalar, but the gradient of Q takes a vector as input and outputs another vector. So this whole thing right here has shape D. And in particular, the runtime of computing it is going to be theta of D. So the runtime of this part in blue is theta of D. And then when we do the entire thing put together, we have this summation right here with this for loop. And so the overall runtime of the whole thing is theta of n times D. For our second order stochastic gradient descent, the only difference is we have this additional matrix multiplication right here. Gamma is a D by D matrix. The whole thing on the right-hand side is a D vector. And so we're going to get our runtime. This multiplication here happening outside of the summation. So the overall runtime will be theta of D squared for the matrix multiplication, plus the n times D for the summation of all of these loss functions right here. So significantly more expensive runtime per iteration right here by a factor of D squared. Stochastic gradient descent, though, coming down here, again, because we've removed this summation, the only difference between stochastic gradient descent and standard gradient descent is that we remove the summation right here. And so now the runtime of each iteration is only theta of D and not theta of n. It's totally independent of the amount of data points that we actually have. The gradient here is going to be a less accurate gradient, but the hope is that we can repeat it many, many times much more more quickly, and that will make up for the fact that this gradient is less accurate. Let's scroll down one more time here to this formula for the second order gradient descent right here, and you get a similar formula for the runtime of now we're dominated, or we have a D computation right here of the gradient, the thing underlined in blue, not including the gamma multiplication. That takes time D times the gamma multiplication, so a D by D matrix times a D vector right here. Overall takes time theta D squared. Notice there's no plus in D right here because, again, second order stochastic gradient descent does not have the summation right here. And so those are the runtimes of each of our iterations. In a little bit, we'll talk about combining those together to with the information about how many iterations we need. Before we do that, though, we're going to go take a look at the pictures, get a little bit more intuition about stochastic gradient descent and what it's doing in picture form. Before I do that, any questions about where we're at? Yes.
Thinking about this stochasticity part of this that relates back to our stochastic vectors and matrices from Peyton.
This is a good question. The question is, we've seen the word stochastic now appear in two different places, one here with stochastic gradient descent and another in the matrix, the stochastic matrix, which is the matrix that we're taking the eigenvector of in PageRank. And the question is there any connection here beyond this word stochastic? The answer is that off the top of my head, I can't think of any meaningful connection here. So I don't think there's a useful connection between the two of them. It is possible to use stochastic gradient descent instead of the power method to solve for the PageRank vector, and that's actually the standard thing to do these days. But so the word stochastic here is only coming up because both of these two methods somehow involve probability. In the PageRank, the word stochastic is because the rows of the PageRank matrix must sum to 1. Here it's stochastic because we're selecting a random data point that we'll use as our gradient instead of doing the full actual gradient. So it's a good observation. Great question to ask, but not a meaningful connection between them. Any other questions? Okay, pictographically, what stochastic gradient descent is going to look like, and I'll do this in light blue. Let's see, I think, is that my only color left available? I think light blue is my most readable color. I'll do gray, that's probably more readable. Starting here from W0, gray is used for the contour line, so I don't want to use gray. We will use light blue, cyan. Starting here at W0, what stochastic gradient descent is going to do is it's basically never going to move in the actual correct direction of the gradient. It's always going to move on some slightly different direction. And sometimes it'll move in a good direction, sometimes it'll move in a bad direction. The farther you are away from the origin, the more likely you are to move in a good direction. But oftentimes you will move totally away from the minimum over here, and even coming back towards your original sample over here. There's no guarantee what your path is going to look like. It's going to go all over the place. But eventually, we do know that eventually it will converge to the minimum. It'll just have a very roundabout path for doing that. Could get towards the minimum and start going away from the minimum, but it'll do something like this, eventually getting closer and closer to the minimum. For the longest time, so stochastic gradient descent has been known since the early 1900s, like 1910, 1920. For the longest time, though, stochastic gradient descent was thought to be just a ridiculous thing to do, that nobody should ever do this when you have the real gradient available to you, because you move away from the origin or move away from the minimum so often. It wasn't until the late 2000s that people actually found use cases for stochastic gradient descent that were not like made up toy examples. Any questions about this picture? Yes.
The direction is random.
So the question is the direction random? And the answer is yes. The reason the direction is random is because the gradient here is random, the gradient determined by an individual point, and the randomness in the direction is the randomness in your data point. That each data point is going to want to move the origin in a different way, or move towards a minimum in a different way. Each individual point by itself will have its own different minimum somewhere in the space of W. And so the randomness of this direction that we're moving in is the randomness of which data point we are considering at each iteration of stochastic gradient descent. There's not like an additional random factor that's added onto that. But because we are choosing one of these data points at random, the overall idea is that in expectation, all of these gradients steps will kind of average out to be the best gradient, the average gradient. And in expectation, on average, averaging all of these steps together, you'll get towards the minimum up here. A plot like this is useful for just getting a rough understanding of like how these different algorithms interact with each other, but nobody would ever plot a plot like this on an actual real world problem. Anytime you see a plot where it has W on its axes, the actual weight vectors or parameter vectors for a problem, these are not things that you will ever be able to observe in a real world problem. These are just a sort of toy visualization of what's going on, trying to get you some intuition for the mathematical formula. But yeah, good question. Any other questions so far?
I might have missed this one. Why would we ever use this as opposed to the other one for a moment?
Yeah, question is why would we use this? The answer is we will get to that here in a minute. Jay, did you have?
I was just wondering if it's important to how the steps are no longer perpendicular to each other the way they were with gradient descent. Is it because randomly sampling
This is a good question. So in the orange line that I drew up here, the steps were perpendicular to each other, and that is almost but not 100% by accident. So here there are actually 3 lines of gradient descent that I drew right here, the orange line, the black line, and the green line. And you'll notice that in the black line and the green line, the steps are not perpendicular to each other. The black line here, they're sort of very slowly curving. The angle is much less than 90 degrees. And for the green line over here, we have a very sharp turn. It's turning almost 180 degrees each time. So one way of thinking about like what should the right step size be would be that you have these 90-degree-ish angle curves. If you are getting 90-degree angles, then your step size, you have a really good step size going on. And if your angles are not 90 degrees, then your step size is off. In practice, that's not a I guess, yeah, so that's from like an algorithm design perspective, something that people think about while designing the algorithm, but not something that people think about like actually as a practitioner, more of an implementer. So that's a good observation, but not directly related to the stuff we're talking about. Does that answer your question? Okay.
like with that with the second order GD, that one, those angles are much less than 90, but it's more efficient. So like saying that angles being 90 degrees means those steps are usually pretty accurately. That is that.
Yeah, and so then the question is, for second order gradient descent here, this magenta line right here, the angles were less than 90 degrees. Why? What's the intuition about why that's the case? If I said that the 90 degrees is optimal, I don't have a short answer to that intuition. Maybe one thing that I will say is that going into all of these details, like I guess all of the things that I've said so far, this is basically like a 10-minute summary of a full semester course on optimization. So I'm not expecting you to be able to explain any of these facts, certainly about like why perpendicular is optimal for gradient descent. It's just a thing that happens to work out to be the case. Yeah.
I have a hypothetical question I
Sure.
can say throughout the class.
Go for it.
I mean, above, if GE and 2G already open, iterating through all the points, could you do something similar to like a triaggling algorithm where you find a single point that would minimize or get you closest to the minimum?
So the when we talked about these runtimes here, these are not yet the runtimes of the overall algorithm. These are runtimes of just a single iteration of the algorithm, and so we haven't yet fully talked about the runtime of the overall algorithm. But the question is, like, maybe we could try not just one step size, but multiple step sizes, or do something very clever at each of these iterations to optimize. And people definitely do those things in practice. And again, that like full semester version of this course would talk about those things. But the high level is, even if you do something fancy, you're still going to need some sort of step size parameter for gradient descent, and you're not going to need it for second order gradient descent. There's no real way to get away from having this step size parameter up here. Okay, all good questions, and I want us to move on a little bit down to this table 1 right here. The idea of this table 1 is that there's 5 rows here. Each one of these 5 rows has one different machine learning algorithm presented. We've talked so far about the perceptron. This is the only one that we've talked about in detail. And it turns out that the textbook also covers this. It turns out that if you squint just right at the perceptron algorithm, the PLA, then it is equivalent to using stochastic gradient descent with this particular loss function right here. You'll notice that every time in this paper the x variable is used, they're wrapping it inside of this phi function. This phi function is our feature map function. So they're being generic over all possible feature maps here when considering each of these algorithms. But so the perceptron, one we've talked about, one the textbook talks about. Adeline here is one of the first alternatives to the perceptron when people realized the perceptron was hard to compute. Adeline was one of the alternatives that people developed in order to actually be able to compute the perceptron. This is really bad in practice. Nobody ever uses it. SVM, I mentioned it in passing at one point when we talked about this loss function right down here. You actually, we plotted in class this loss function. It turns out to be a surrogate for the 0-1 loss and extremely, extremely similar to the logistic loss. You'll notice that it was invented by Vapnik, so the VC dimension guy, and this other person named Cortez. Cortez, I'll bring up her picture since we haven't had a whole lot of female inventors yet that we've talked about. She and Vapnet together invented this SVM, which amounted to inventing just this one single formula right here. And she is now a vice president of research at Google. We will talk more about the SVM in detail in a week or two. And then we'll also talk more about this lasso method in a little bit. So these are just examples of different loss functions here. These days, every machine learning algorithm is written in terms of just a loss function and then what optimization algorithm you're going to do to solve for it. But when this paper first came out, 2011, that wasn't fully the case. People were still talking about having a separate perceptron learning algorithm or a separate SVM learning algorithm. But nowadays, nobody does that. Everybody just talks about here's the loss function, and then one of these 4 algorithms is what we use to learn it. Okay, section 3 over here. This is where the stuff is going to start getting interesting and where we'll do the actual calculations of how long what the actual final runtimes of these 4 algorithms is. This first paragraph right here is another just description paragraph of things that we talked about in our textbook. So it's summarizing the relevant parts of chapters 1 through 3 of the textbook down into this one paragraph right here. And then 3.1 new stuff. We're going to talk about 3.1 in the notes here in a second, but the first thing that I want to do is highlight that they identify 2 different scales of problems that are important. Small scale learning problems and large scale learning problems. And in a small scale learning problem, the idea is that our number of data points is relatively small. So it's the capital N small. And this is equivalent to saying that the amount of computation that we need for our problem is small. Or that we're not limited by computation. There's not going to be any formal definition, not limited by computation. There's not going to be any formal definition about the boundary of these 2 problems because they will change as computers get better and better. So when this paper was first released in 2011, N being small meant something different than it does today, where computers are now more powerful. But there's some transition where your N is small and so not limited by computation. And what we will end up seeing is that 1GD or 2DG will be the optimal algorithm. 1GD, 2DG will be optimal. And another preview of what we will see here is that 2GD always better than 1GD by VC theory. So if you're on a actual learning problem, then you'll always want to use second order gradient descent instead of standard gradient descent. And you'll use those whenever N is small. And then large scale machine learning problems, this will be the case when N is large. Here, and large, and that's equivalent to saying that you are limited by computation. That so say you have trillions or more data points where you don't even have time, maybe even to consider every data point once. That's the situation of N being large. Limited by computation, and it will turn out here that 1 SGD is always the best algorithm in this case. So we're gonna transition here to doing a bunch of pictures and calculations in order to demonstrate this, but this is the end takeaway. The thing that you absolutely have to understand for this course is that if you're in a small scale learning problem, which meaning you are not limited by your computation at all, then second order stochastic gradient descent is what you will want to do. But if you are limited by computation at all, then first order stochastic gradient descent is what you will want to do. That's the big picture takeaway. Question?
Why is CGD always better?
Yeah, so great question. Why is this the case? That's what we will talk about. Yeah, so it's totally appropriate to not understand why this is the case. This is like the topic sentence of the rest of the class here, explaining these things. Okay. So I'm going to start with this problem-free visualizing the optimization error here. And this is the part that's going to review a little bit of your stuff for this coming midterm. We're going to talk about the different statistical errors and then see how the optimization stuff fits in with these statistical errors. There's 3 graphs that we're going to end up drawing here. The first graph will have our n value on the x-axis like this. The second graph will have our w values on the x-axis like this. And the final graph down here will have time on the x-axis. All 3 of these things are things that you'll see people draw, and you'll need to be able to understand exactly which one is being referred to at any given time. But these are going to be the 3 important graphs for understanding this optimization here. We'll start with this middle one here, that it's most similar to the graphs that we had above. And here we have we've already drawn this sort of graph where what we're visualizing here is our E sub n, our in sample error right here. And this is the thing that we're trying to minimize. And if we are able to run our computations for forever, then we will get to this minimum right here, this minimum value. But we are in practice not going to run our computations forever, and we're going to stop at some particular point. So I'm drawing 3 dots right here. This first one right here, this is our starting W naught. And so this is what our loss starts at some point that's particularly high. And then we're going to run our optimization until we hit this point right here. There is no, in the textbook, definition for this point right here. And in Lian-Bateau, they talk about this as being F tilde sub n. Again, one of the things that the textbook does do and that we've done in class so far is talk about there's this bijection between our functions and the parameter space. And so whether we are talking about an f or an h, one of these functions, or talking about a parameter, it's like the same thing. So here, this f sub n with a tilde on top of it, this is somehow representative of some particular w parameter. And then the minimum over here, the actual minimum of our optimization, this is what the Lian-Bateau calls just f sub n. For Lian-Bateau, anytime there's a tilde on something, that this indicates that it is somehow related to optimization. And this difference, use gray right here. This difference between our f tilde sub n and our f sub n, this is the optimization error. Forget how to spell optimization, so I'll just use the E sub opt, which is the notation that Lian-Bateau uses for this value right here. And so this is a new type of error that the textbook hasn't discussed at all, and we haven't discussed at all. Another way of visualizing this optimization error is with this axis of time. And here there is, I'll do it in magenta. It's a different curve than this red curve up here. But we're starting at some particular location. And this is our En of F tilde sub n, that as we add more and more time to our computation, our in-sample error of this F tilde sub n is going to get smaller and smaller. So we're starting up here from E sub n. This might have taken like 10 time steps to go from this location down to this location. And maybe it would take another 10 more time steps for us to go from this location down to this location. This E sub n right here is as we vary time, how is F sub n changing? It's not going to converge to 0. It's going to converge to some to another value, and this other value is our E sub n of F, and in particular, it's this value right here. This dotted line right here is this where we're converging to in this time plot. So as time goes on, this in-sample error of F tilde sub n will approach the En of F sub n. There should be a subscript n right there. In all three of these cases, I've written E in with E sub I n, and so that's the textbook's notation. Leon Buteau, again, is the E subscript n for the in-sample error of F tilde sub n. The black over here is the Leon Buteau notation. The magenta over here is the mixture of Leon Buteau for F tilde sub n, but the textbook for in-sample error E sub n. So these are the new errors that we'll have to think about in terms of optimization. And this top plot is the one that's, I saved it for the top because it's going to be the most important of these plots. And it's going to relate this optimization error to all of the other errors that we have seen so far, like the generalization error, and the out-of-sample error, and the in-sample error, and so forth. Any questions about these two plots before I go into the top plot?
What was the black again?
The black over here is, so the only difference is I do not have the letter I in front of N. So the black right here using the Leon Buteau in-sample error, the magenta over here using the textbook in-sample error. Okay, this top plot is, we're going to start with a plot that we have seen before, and that is that as our number of data points increases, our in-sample error, En, is going to increase. And I'm going to use a mixture of notation from the textbook and from Leon Buteau. There's never a conflict where the same thing means the same letter or the same phrase means different things in the two papers. There's only a situation where the same concept has multiple names, so it shouldn't be ambiguous. But here, the in-sample error, I sub n, so it's the textbook's version instead of Leon Buteau's. And the out-of-sample error, converging like this. This is our E sub out right here. And what we have bounds for that we've talked about is this generalization error right here. This is our generalization error. And the only technique that we have of talking about our out-of-sample error right now is our in-sample error plus this generalization error gives us a bound on our out-of-sample error. Again, it's the VC dimension that controls this generalization error. And so there's some trade-off between having our generalization error small and our in-sample error being small. Both of these two lines, the out of sample error and the in sample error, they converge to each other when n goes to infinity. And the limit, as we have an infinite amount of data, our in sample error and our out of sample error will be the same thing. That error is called the approximation error. And your homework, which was due last night, everybody, by the way, who submitted it by last night got full credit. Those of you who haven't submitted it yet, please still submit it. There's the small late penalty for submitting with a small amount of time late, but the late penalty goes up exponentially. And this line that they are converging to, this is called the approximation error. And section 2.3 of the textbook, which we mostly skipped, is where this plot comes from. I think we've drawn this plot at least once, maybe 2 or 3 times, and this is about where we stopped for this plot. In the Leon Buteau paper, coming over here to section 3.1, they introduce their version of the approximation error, and these two things called the estimation error and then the optimization error, which we've already talked about. So let's see how their approximation error and estimation error fit into this plot right here. The first thing that they do is that they identify the Bayes error. And their notation for the Bayes error is E of F star. This is the Bayes error. F star, again, is the best possible function. So F star is the argmin over F of E sub F. This E without any sort of subscript is the out of sample error in the Leon Buteau notation. So this is the Bayes error, the best possible function, or this is the Bayes function or the true function right here. The error is applying the error to that. The function that minimizes our out of sample error, that is the Bayes error right here. We know that this in this graph, this problem has noise inside of it because this Bayes error is non-zero. That's equivalent to saying that the problem has noise in it. And they identify this distance right here as their version of the approximation error. This is E app in the notation over here. E app is E F star minus this E F star F. The E app approximation error. In your homework, the way I defined approximation error in the homework, it's this gray line down to 0, but in the textbook, it's this gray line down to the black line right here. Another quantity that's useful for talking about this approximation error is they talk about in Leon Buteau this F star subscript F, which is equal to the argmin of F contained in big F of E of F. So the only difference between this gray F star sub F and this black F star without the F is that this is the function restricted to whatever our hypothesis class is. And this value right here, this is dash dash gray line, is in the Leon Buteau notation, the out of sample error of F star sub F like that. So this gray line right here, this E F star F. The approximation right here, error right here, the difference between the gray line right here and the black line down here. Going back over to the paper, you can see that the gray, this part right here is the gray, and this part right here is the black. So their approximation error is the difference between those two things. The next error they're introducing here in 3.1 is the estimation error. That's this distance right here. I want to change my color. Let's do this in orange. This is the E-est, the estimation error right there. And this is the difference between our out of sample error and that approximation error. The out of sample error, the way we talked about it in the textbook, is always just E out with no function being applied to it. But for the Lian-Buteau notation, they are using E with F sub n right here. The F sub n, this is similar to the G in the textbook notation. G in the textbook notation, basically always suppressed, almost always suppressed, and just writing E sub out. So when it has E F sub in Lian-Buteau, that's equivalent to the E sub out in the textbook notation. And again, this F sub in, this is the minimum of our particular optimization problem for whatever parameter space that we're looking at. That's our estimation error right here. Coming back over to the Lian-Buteau paper, this E F sub in, that is the orange part right here. And then it's comparing the orange part to the gray part, comparing that orange part to the gray part right here. So comparing this orange thing to the gray thing, that gives us our estimation error. Then the last thing that is included in the Lian-Buteau analysis that's not at all in this picture yet, not in the textbook, is there's an additional line up here that is our optimization error. So between our out of sample error for Fn and this dotted black line up here, that distance is our E opt. And this is the distance, this is our out of sample error E out on that F tilde sub in. So this E opt on the black right here, the black on top, that is this distance right here, from our F tilde sub in down to the best possible error. This is the only thing, this is the only error term that relates to computation in any way. This is the only error term that relates to computation in any way. So this is the only error term that's actually really new to us. And this estimation and approximation error defined slightly differently than the ways we talked about it in the textbook, but essentially the same, essentially capturing information that we have already talked about from the textbook. Any questions about anything in these pictures?
Can you clarify which one is approximation error? So you have gray dashed line and then you have this.
Yeah, so this is a really good question. The question is that I have called two different things the approximation error. One of the things that I've called the approximation error is this gray dashed line right here, which in the Lian-Buteau notation is this E of F subscript EF star. And this is the way the approximation error is defined in your first or in your homework that was due yesterday. The other way the approximation error is defined is as the difference between this line right here and this black line down here. And the question is, which one of those is the actual approximation error? The answer is that half the world calls the gray line the approximation error, and half the world calls this difference black thing the approximation error. And there is no standard. The only sort of standard that people agree on is that if you write down the equations, then people will understand what you mean. Semantically, like this gray line and the difference between the gray line and the black line capture the same information because one of them takes into account the Bayes error, one of them doesn't. But they both capture the information about what are out of sample versus in sample errors, what they're converging to. So that's why they're both called the approximation error. And you will see people talk about both of these as the approximation error equivalently. Lian-Buteau, for the most part, uses this gray line right here as the approximation error. He specifically defines E sub app as Lian-Buteau, for the most part, uses the difference between the gray line and the black line as the approximation error, and he specifically defines E sub app as that difference. but you, including even in his paper where he defines the approximation error as this difference, he occasionally talks about the approximation error only as this term right here, not the difference. So legitimately confusing thing that this one English term has multiple definitions. If you need to be unambiguous about which one you're referring to, then you have to go to the mathematical definition and write out the notation. Does that answer your question? Yeah, maybe not satisfyingly, but that is the answer.
If you asked us about it, which one would you?
Question is, if I asked you about it, which one would I want? And the answer is that you should be able to infer from context which one I'm talking about. And if it's not obvious from context, then you could ask me like, okay, what's the actual formula? In which case I can provide the actual formula. If it was important, then I would provide the actual formula. Yeah, yeah, the short answer to which one should you think of if I use that word is you have to infer from context. We have one situation like this that we have seen so far where we've had to infer things from context, and that's in terms of the generalization error. Lian-Bateau will also, well, let's see. So in our textbook's notation, the generalization error is specifically on this curve with model, complexity. We had our in-sample error coming down like this, in-sample error, and our generalization error going up like this, generalization error, and our out-of-sample error being this thing, E out. Lian-Bateau and a lot of other people will also call this out-of-sample error the generalization error. And you just have to sort of infer from context about which one of these two like concepts the term generalization error refers to. In this class, I will always use generalization error to refer to the difference between the out-of-sample error and the in-sample error. But in the paper, Lian-Bateau goes back and forth. And in the real world, people do go back and forth between generalization and error, and meaning the out-of-sample error, and generalization error, meaning the difference between the out-of-sample error and the in-sample error. Two reasons for this. One is that it is a very new field. So again, when this paper first came out, I was in the middle of my PhD, but this paper is now foundational to the field, and you can't do data mining without understanding stochastic gradient descent as presented in this paper. And so because it's such a new field, there just hasn't been a standardization on terms yet. Everybody agrees in calculus what the derivative is because we've had 400 years of working with the derivative, and but we've only had 10 years of working with stochastic gradient descent, and so people are still up in the air about what's the right terminology for things. That's one reason why terms are ambiguous. The other reason why terms are ambiguous is because if the English term is only ambiguous mathematically when the mathematical expressions calculate somehow the same important information. And so the out-of-sample error right here, this generalization concept right here somehow captures the same information as the out-of-sample error once you combine it with the in-sample error knowledge. And similarly, the approximation error here as just this dotted gray line by itself, that somehow captures the same information as the approximation error of the difference between the gray line and the black line. So because those terms mathematically are so similar to each other, people will just use the same English expressions to refer to them. But it is legitimately confusing for people who are just getting started in the field. One last thing that I will say about this is the reason these papers have this short, like one paragraph introduction always about what their notation is because every author and every paper everywhere in the world will use notation slightly different than somebody else. And so it really is necessary to define the mathematically what each of those terms mean for that situation. I apologize, I'm 10 seconds over time, so we'll end here and continue on Wednesday. If anybody has questions about anything, then I'm happy to get those answered right now.